When a commercial aircraft is lost, the investigation doesn't begin with blame. It begins with data. Every fragment, every wire, every recorded parameter is treated as evidence. The goal isn't to punish, it is to protect. We must find the exact chain of failure to ensure it never happens again. Let's clear up the myths immediately. First, they aren't black. They are painted international orange for maximum visibility in wreckage. Second, there is never just one. Modern aircraft carry two independent recorders, the CVR and the FDR. Together, they preserve the final moments of a flight with forensic precision. The cockpit voice recorder captures 4 isolated audio streams. You have the captain's headset mic, the first officer's mic, a third crew station if equipped, and a dedicated area microphone mounted on the overhead panel. This area mic picks up ambient sounds, alarm chimes, switch clicks, engine spool changes, even casual conversation. It records continuously on a 2-hour loop. When time expires, it overwrites the oldest data. That is why recovery is time-critical. A flight data recorder is the aircraft's digital memory. Modern units log over 2,000 parameters at 1-second intervals. Airspeed, altitude, attitude, control surface deflection, engine N1 and EGT, fuel flow, autopilot engagement, warning system activations. It stores a minimum of 25 hours of flight data. When synchronized with the CVR, investigators can reconstruct not just what the aircraft did, but what the crew saw, heard, and knew. And they are engineered to survive the unsurvivable. Certification standards require them to withstand 3,400 Gs of impact, 1,100 degrees Celsius for 60 minutes, 20,000 feet of underwater pressure, 30 days in salt water. They are mounted in the aft fuselage, the most structurally protected zone, because their purpose isn't to save this flight. It's to save the next one. The moment the site is secured, the forensic clock starts. Investigators establish a GPS referenced grid. Every piece of debris is photographed, tagged, and logged. A fractured hydraulic line can reveal a pressure rupture. A melted connector can point to an electrical arc. Even soil discoloration can indicate fuel ignition patterns. Nothing is too small. Then comes reconstruction. In a controlled hangar, teams rebuild the aircraft from recovered fragments. It's a 3-dimensional puzzle. The pattern of damage tells the structural story. Did the wing separate in flight? Fracture surfaces show the difference between fatigue cracks and overload failure. Did the tail break first? Burn patterns reveal fire origin and propagation direction. The wreckage doesn't lie. It just needs to be read correctly. If the aircraft goes down in water, the underwater locator beacon activates automatically. It emits a 37.5 kHz ping for 30 days. Sonar vessels map the seabed. Remotely operated vehicles retrieve the units. They are transported in shock-absorbing cases to specialized labs. Inside clean rooms, technicians extract the solid-state memory. No power is applied until data integrity is verified. Data extraction is meticulous. CVR audio is filtered, enhanced, and transcribed by trained analysts. Background noise is isolated. Alarms are timestamped. FDR parameters are converted into readable graphs. Then both streams are synchronized to the millisecond. At 14:32:18, the stall warning activates. Airspeed drops to 98 knots. Pitch attitude climbs 15 degrees. Thrust levers advance to maximum. Every action, every system response is locked to a single timeline, but data alone doesn't explain why. Investigators cross-reference flight records with maintenance logs and air traffic transcripts. They look for deviations. Was a sensor replaced recently? Did weather deteriorate faster than forecast? Was there a known bulletin about this system? The timeline becomes a map, and the map leads to the cause. Accidents are rarely caused by a single failure. They are caused by alignment. This is the Swiss cheese model. Each slice represents a safety layer. Design redundancy, maintenance checks, pilot training, automation safeguards, air traffic control. Each hole is a weakness. When holes line up across multiple layers, the hazard passes through. The investigation's job is to find every hole and understand why they aligned. No single person solves an accident. Teams are multidisciplinary. Structural engineers analyze metal fatigue. System specialists trace electrical and hydraulic logic. Meteorologists reconstruct wind shear and icing conditions. Human factors psychologists examine decision-making under stress, and pilot advisors simulate the cockpit workload. This isn't about judging choices. It's about understanding the environment those choices were made in. Every hypothesis is tested in certified simulators. Investigators fly the exact scenario. Could the crew have recognized the failure earlier? Was the procedure ambiguous? Did automation mask a developing problem? Simulator runs reveal whether the outcome was inevitable, or if a different input could have changed it. This isn't hindsight. It's empirical validation. Human factors are examined systematically. Fatigue degrades situational awareness. Automation surprise occurs when systems behave differently than trained. Confirmation bias leads crews to dismiss contradictory warnings. Crew resource management breakdowns prevent cross-checking. Investigators don't ask, why did they make a mistake? They ask, why did the system allow a mistake to become catastrophic? The answer is never just pilot error. It's always a systemic gap. If we stop at blaming the individual, we learn nothing. We must look at the interface between human and machine. Did the warning make sense? Was the training relevant? Was the culture supportive of speaking up? These questions turn tragedy into a lesson. And that lesson is what saves lives. The investigation concludes not with a verdict, but with recommendations. Major accidents typically produce 10 to 20 formal safety directives. They go to regulators, manufacturers, airlines, and training organizations. They are public. They are trackable. And they are mandatory. This is where data becomes design. History proves the model works. The DC-10 cargo door failures led to redesigned locking mechanisms and mandatory inspection protocols. TWA Flight 800's fuel tank explosion mandated nitrogen inerting systems across wide-body fleets. Air France 447 revealed critical gaps in high-altitude stall training, triggering global simulator curriculum updates. Every tragedy forced a structural change. The systems pilots rely on today were born from accidents. TCS collision avoidance came from mid-air collision investigations. Ground proximity warnings emerged from controlled flight into terrain events. Predictive wind shear radar was developed after microburst encounters. Even modern checklist philosophy and crew resource management training were forged in failure. We don't just remember accidents. We engineer around them. The result is measurable. In the 1950s, the aviation accident rate was roughly 40 per million departures. Today, in 2026, it is less than 0.1. That is a safety improvement of over 900%. Not because pilots got perfect. Not because engines stopped failing. But because we built a culture that learns from failure. So when you see a black box, don't think of it as a recorder of a disaster. Think of it as the guardian of the future. It is the voice of the past speaking to the engineers of tomorrow. It ensures that no matter what happens in the sky, the knowledge gained will keep you safe on your next flight. Thank you for watching.